Hi everyone, I'm Matthieu. I'm the AI coordinator at IGN, the French National Mapping Agency, and I'm really thrilled to be here and I will try to share a concrete perspective on what AI actually looks like in practice in our setting and how this concrete experience reveals broader challenges that we need to tackle, whether ecological challenges, social challenges, strategic, political challenges. I want to start from something real rather than a very abstract discussion. I think that too often when we talk about AI, we stay at the level of generalities and of myths and of enchanted promises. And I'd like us to build from a shared foundation on what AI systems actually are, and real systems, existing systems that we can examine and understand. And from there, we will see the challenges that stem from this point. So my approach will be in two parts. First, I'll take some time to provide context and share with you what we are talking about when we are talking about using AI in the context of geographic data production. And then we'll zoom out to examine the broader implications from local to global scales. So some context first. Of fundamental challenge at IGN and independently from AI is that the territory is transforming, and it's transforming fast. Many ecological dimensions of the territory are changing really fast. It's transforming under the effects of climate change, under the effects of anthropogenic pressure, and it's transforming faster than it has ever before. To maintain collectively as a society or grasp on this transformation, we need to know what's happening. And we need new descriptions of the territory that are both fine-grained and that are regular, that are made on a regular basis. We need to track phenomena like forest evolution, coastline evolution, land cover, and land use change, and we need to monitor all this. We will focus on these first examples. That's not the only one, but that will be the main one I will be talking about. And that's land cover mapping, especially tracking soil artificialization. So when you convert agricultural or forest soils to urban use, for instance, you lose a lot of ecological functions of your soil in ways that aren't easily revertible. French legislation has set the ambitious goal of zero net soil artificialization by 2050. And IGN, we have the role of producing the reference public data that measures and track this change in soil, in land use and in land cover. So what does AI enables us to do in this context? Well, AI gives us something just like what you are seeing on this picture. That's a land cover map produced by AI. This is a high-resolution aerial image. Each pixel is 20 centimeters wide. And those photos are acquired by IGN every 3 years. So we take 3 years to cover the whole national territory, but we have this high-resolution imagery at this frequency. Superimposed on this image, you have an interpretation, a first analysis of what's in the picture. And on each pixel of this image, we have provided a classification, a first semantic description. And so you can see buildings, deciduous trees, conifers, water surfaces, impermeable surfaces, and so on. The main message is this isn't perfect. We couldn't use this directly as a public reference data. There would be too much variability, year-to-year variability, for instance. If, for instance, we take the picture of the same area 3 years later, and just maybe not in the month of May, but in the month of July, then just the trees might be a little smaller or a little larger, and we'll see changes that do not correspond to anything on the ground. You have some defaults. The buildings might not have really sharp angles, or there might be some discontinuities in the road network, and so on. So if you have the eye for it, you can see there are defaults. That's expected, but we would need something more robust to serve a public policy. But yet, we have made a big step forward with compared to when we only had the image. We have a lot of information on what's actually on the ground. So we have a first foundation on which we will build. How do we obtain these models, these image analysis semantic segmentation models? Through machine learning, of course. And what does it mean that we are obtaining these models through machine learning? It means that we are building large training datasets that create the links between the inputs and the outputs that we want in our algorithm. So we build large corpuses of photos and land cover maps that are made by hand, that are made by humans, and those are used to train models that are deployed on larger scale on the national territory. The real difficulty is not to have a model that performs image analysis in the way I showed you just before. The real difficulty is having a good model that is able to read imagery in all of the contexts it should. We want our land cover models to be able to work in cities, in forests, in agricultural areas. We want them to be able to perform equally well in the Vosges forests and on Mediterranean vegetation. We want it to perform equally well on slate roofs or on tile roofs. We want it to perform equally well on photos that were taken in the months of April or in the months of July. And once again, vegetation does not look the same in every month throughout the year. And so the diversity of this reality, landscape, geography, acquisition conditions, our model must be capable of managing it. And in order to do this, we need to provide massive, large-scale, high-quality, and highly diversified training datasets. So what you see on the top right part of this slide is a map of continental France. I hope that you recognize this. And each red dot on this map is some kind of area of an area of the kind you're seeing on the left. It's an area of maybe 1 or 2 squared kilometers, where a colleague, a human photo interpreter, an expert of image analysis by human means, has provided the land cover map. We have sampled all over France areas of this kind to cover all the diversity of the situations our models have to work in. In total, there are 2,500 squared kilometers of land cover maps that are produced this way by human means in order to train models that will be deployed on the French territory that is maybe 5,500,000 squared kilometers. So we have multiple orders of magnitude between the size of our training data sets and the size of the French territory on which the models are applied. And this scale effect and this change of scale effect is fundamental. That's the real reason why we are using AI, because we manage to gain speed, to gain productivity, because we have this scaling effect that is really clear on the surface side. It evolves. So just to zoom, I want really to show you all the steps, what's really behind this kind of systems. So it's not just about models, as I told you, it was about training data. And so you have a quick overview of the pipeline that this training data sets creation goes through. We start from the image, we segment through algorithm means the areas in small polygons that are homogeneous from the radiometric perspective, and then a human annotates those polygons to say, oh, here's this building, it's an agricultural area, and so on. Once we have these massive, diverse and high-quality training data sets, we get models that produce AI land cover maps across the French territory. But actually, so here you can see the application of the inferences of our land cover models on the whole French territory. But it doesn't stop here, actually. We need to provide, I told you it would not be a good public reference data, so we need to build reference data that is more stable. So we cross-check image analysis with other geographical databases we add information that is not visible in images. For instance, is this building used for residential or tertiary or industrial purposes? That's not something that you can read from the sky. So we have to get this information elsewhere. There's no magic, once again, in AI. So AI is part of a broader process, and with more technical parts, more algorithmic parts, and also more human work. Annotation of training data sets, but also complementary annotations downstream and quality assessment and quality control at the end of the pipeline. This territorial description goes beyond land cover mapping and artificialization tracking, and so I will not dwell upon the details on those, but a similar approach can be used for forest mapping, for agricultural mapping, for 3D mapping with LiDAR data, and so on. So it's really quite general, actually, what I just showed you with land cover. And just so that you can see the whole pipeline, and to connect with the theme of today, that is open source, we have made on all this pipeline on all this AI pipeline, openness as a core principle. Everything, actually quite everything is open. The final public reference data, the raw results of our AI models, the training data sets, the trained models, the methods we used to build those models, those data, the training engines, everything is open source, open data, and is on in the public sphere. So that was the first part where I gave you some context of what's AI like at IGN. Just a quick mention: when we open source training data, quite often our data sets are amongst the leading data sets worldwide. There are not that many high quality, diverse data sets for ecological purposes in Earth observation and that are suitable for AI. So really that's a scarce resource today. So that was the part for the context, and now I want to navigate through many challenges that this poses beyond the scope of the sole IGN. What's quite difficult with AI is that it mixes a lot of actors, a lot of problems and scales. So we'll have to navigate through multiple reading grids, ecological footprints, social issues related to work, organization, and sovereignty and strategic autonomy concerns. And we'll go from the most local scale to the most global scale to try to see how all these issues are intertwined and how they translate at each of the scales. So let's start from the most zoomed in level, and that's the technical system itself. That's the models, the servers, the computing components. The most pressing issue at this level is that AI consumes energy. That's quite material. We need GPUs to train and to run deep neural networks, and we have to build those components, and they have to be fed energy both to run and to be cooled. And we know that these are quite significant energy consumptions. Orders of magnitude may vary greatly. When we talk about training GPT from ChatGPT, we are talking about hundreds to thousands of tons of carbon equivalent to train those models. In our case, training state-of-the-art models for Earth observations is more like less than 1 ton of CO2, less than 1/100th of a ton of CO2. So not everything can be put in the same bag concerning ecological footprint of AI. But still, there is a subject, and there are actually levers to limit this ecological footprints. The first one is sobriety. You can always question, is it relevant to use AI that is quite energy intensive in this context? So in some cases, maybe human work or maybe an alternative technical solution will be more effective and more energy saving. The second lever is through efficiency levers. You can, and that's just one example. I won't detail too much, but you can build either very general models that will be able to work throughout a lot of contexts, a lot of kinds of data. And in the context of IGN, we work with images, we work with time series of images, photos that are taken every few days by satellites. We work with radar data, we work with 3D data, we work with historical images taken many decades ago. And if you want the same models to be able to operate throughout all these kinds of data, well, you have to build really large models that will be able to learn all this diversity. And this will be quite power consuming. If you provide architectures of neural networks that are more suited to your specific problem, then you can really reduce by orders of magnitude the footprint of your models. And finally, there may be also third level a trade-off between the performance and the ecological footprint. Quite often there are scaling laws, and you might have to double the size of your models and the consumption of your system to gain one more point of performance. And that's not in many real cases necessary. Actually, there is often a trade-off where you don't have to go throughout all the maximum size of your models. Zooming out slightly, AI inserts in. We saw earlier that it inserts into broader work process. It's not just about the models; it's about the model and work that is performed by humans. And there are several problems that emerge here. The first is the classic automation question: what do we want to automate? The usual responses include productivity gains, automating tedious work, concentrating on creative parts of the work, but it's only the problem. Who gets a voice in these decisions? Who gets to say what is tedious work? Should tedious work actually be done? It might be a relevant part of human work. And I think, well, to me, it seems that it should come from people doing actually the work. They should have a prominent voice in these kind of decisions, because they will be the ones impacted most in the work that is still performed in using those AI systems. There's also linked to this automation problem. We see that we have the link between your work and the result of your work is lengthening. Before, the colleagues who performed image analysis could point to a piece of data that is produced and say, I worked on this part of the territory. And so there is a clear link between my work and what is produced. Now it goes through, I built a training sample that was used to train a model that was used throughout the whole national territory. That made the final database. But you have, if you want to provide meaning for the work, you have to provide new ways to say that there are high quality or low quality training data sets, and that those are valuable work outputs. And I think that there's a lot to do in this area that we at the IGN have not invented yet. So that's still a relatively static view: what to automate, what not to automate. I think that there is also a fundamentally dynamic problem, and that's a viability problem. When we train, or I will take the example of using AI to map forests. For instance, on the left, you see you want to be able to recognize on those photos whether you have oak trees, whether you have pine trees, which kind of pine trees, and so on. That's if you are able to do so, please tell me, because it's really hard. I've provided the correct answer, but that's expert work, actually. So we rely on expert work to provide us the samples, the training data that we'll be able to train our AI systems. But how did our experts become expert in the first place? Mainly performing the actual work we are using AI now to do on a large scale. So it's like it might be as if you were automating all apprentice work. You know, you have to provide. You use masters to provide guidance to the systems that replaces your apprentices. But then, where will come the experts in 10 years? Again, we do not have the answer. We know that there is an important issue here, and that's the equilibrium that you will reach just considering the optimal locally the optimal training data volume is not as no theoretical reason to be the same as the amount of work you have to provide to reproduce on the long time. On the long term, your ability to feed those AI systems, because we will need in the future to still feed those AI systems. It's not done once and for all. You still have to provide new examples or to adapt to new sensors, new conditions, and so on. So that's really, I think, an important point that is not seen if you only consider the very short term. And we have a tendency, I think, in AI to overlook to look too much on the short term and to overlook the long-term issues of the systems we are building. Zooming out one step further, there are also important dynamics that happen at the field of the AI field levels. The AI research field functions largely through benchmarks. Advances happen by showing that methods are perform better than state-of-the-art on established problems. What's considered at a given moment a relevant problem is extraordinarily dependent not only on the state of scientific knowledge, but also on available data and available data sets that have reached the benchmark status. I think it's really more intense than in other scientific domains that this feature. So if we want the models that we discussed earlier, if we say the ecological footprint of AI might be contained with small-scale models that have a view towards limiting their energy consumption, well, we have to provide relevant data sets and relevant academic settings in which this is the questions that we pose. And you cannot influence the research agenda if you don't provide data sets. So open data plays really a key role in shaping the dynamics of the AI as a scientific and as a technical field. We also have major concentration issues because the AI field is concentrated with really a small number of hegemonic digital actors, and in many cases we face reproducibility issues. Many systems aren't open. We don't know how GPT was trained. We don't know what's the corpus, what's the training data set behind GPT. And this has a negative consequence, that is that the field may evolve toward increasingly resource-hungry models, making contribution and replication very difficult for actors without access to large-scale computing infrastructures. And that's a positive feedback cycle that is actually quite negative, because it tends to foster innovation in the direction of more and more, ever more consuming models and techniques. Once again, open source is most fundamental, because open source, open models, open data sets, as we see in our IGN setting, it helps broaden the game. It helps new actors to hop on the AI trend and contribute to the development and to shaping what AI systems are actually in use. So, because you reduce the barriers to entry, you have to provide less training data, less compute capacities if you already have good AI open assets. So that's really a systemic consequence of the open source that is, I think, key in this context of the dynamics of AI. And zooming to our largest scale, and that's where I will end for today. Oh, okay, no. No, see, okay, that's here that I want to say you this. Once again, at the macro scale, the energy sectors and the AI sectors are more and more intertwined. I have mentioned consumptions at the local scale, at the scale of a model. But if we aggregate, we know there is a recent report from the International Energy Agency that tells us that overall the consumption of data centers, it's 415 terawatt hours, so that's 1.5% of global electricity demand, and that will be doubling by 2013. And largely, this dynamic is mainly due to increased use of AI, or in a large part due to an increased use of AI. So it's really not neglectable. It's not the main use of electricity, and will not be the main use of electricity, but it's really quite significant. We have efforts to regulate this, to monitor this, to methodologies to assess the ecological footprints of AI systems, whether on the carbon footprints, water consumptions, metals consumptions, and so on. But we lack information. Once again, a lot of the relevant information is closed. Manufacturers, AI suppliers do not share important features of the AI systems they built that would be required not only to know their own footprints, but also the footprint for every provider that builds upon their capacities. So really, we lack a lot of structuring informations on this. And the last point is about strategic autonomy. Geopolitical rivalries are deploying throughout the AI field. And once again, open source is key. I often hear that open source might just be gifts to rivals east or west. And I think that's quite a wrong view. In the case of the AI sector, we do not have the biggest competitors yet, and big tech companies, big American tech companies or Chinese tech companies, they do not require our open data to be able to build their own private models and data sets. So opening these assets actually differentially mostly helps the European ecosystem, and it helps broadening the competition. And so I think that it's really an important industrial strategy for Europe and for strategic autonomy in this context. So just to sum it up, I hope that I have showed you, I do not provide definite answers. I provide you a view of where we are, what actually are AI systems at the IGN, and a whole lot of issues that are raised and some pieces of answers, one of the main being open source. But the main message is the future of AI isn't written yet, and there is really a possibility to discuss it, and open source is the main way to discuss this and decide what this future is democratically. Thanks a lot for your attention.